This is probably you right now. Hotshot out of AP Chemistry. Kinda knows chem, but not really. There are some things you might know though. Hybridization and MO diagrams should be easy stuff for you by now. But there's one more topic that are related to these called the pi system. And that can be a little confusing sometimes. But that's okay. This video will help you understand the pi system and what it looks like, what it's used for. So sometimes you'll be asked to draw molecules or understand molecules that have a particular arrangement, and that arrangement is the conjugated double bond and single bond system. So look at this molecule where there's alternating double and single bonds. Normally we'd think from first glance that the pi electrons, those that create the double bond according to valence and molecular orbital theory, would just be contained within these double bonds. But that's actually not true. When it comes to pi electrons, they are spread throughout the molecule. But this can be in a variety of different arrangements depending on how many electrons there are and what the energy level is. And they all look different in the physical world. So let's start with a simple molecule like this 1,3-diene over here. So first we start with the all-important energy arrow because we are building these arrangements from the lowest energy level. So starting from the bottom, we'll first imagine that none of these p orbitals combined in anything. They're just plain p orbitals in an atom, or taken from all these carbon atoms. And we'll just draw them in a line. So to represent the phase of these p orbitals, each of these p orbitals is holding one electron. To understand the phase, or to represent them, which is one of these electrons' wave-like properties, we will color these p orbitals. So we'll make one side black. Now notice how in this arrangement, which we will call pi 1, all of the lobes are facing the same way. All the p orbitals are facing the same way. So if I were to draw this molecule, if these were the 4 nuclei, the 4 carbon nuclei, these 4 lobes will undergo constructive interference. They'll combine and create one lobe. And the same goes for the bottom. And here we have our subway sandwich of a molecule. But sometimes you want to split your sub down the middle, and that's where some of the other arrangements come in. So we have pi 2, where 2 of the p orbitals are facing the same way, and the other 2 are not. And at this site we have destructive interference, where these nodes are canceling out, or sorry, these lobes are canceling out, and this area is called a node, a place where there's a very low probability of finding electrons. Now to draw it out in the same way, you can imagine those lobes that face the same way will combine into bigger lobes. And the same for this bottom area. But where the node is, there is no electron density. That's how it looks in a line. But if we wanted to draw it on the actual molecule, we imagine this is how the molecule looks. We would take the lobes and just apply them directly. So if you look where the node is, it's after the first 2 carbon atoms. So there's 2 carbon atoms over here, a node where we'll find no density, and then we'll draw them in like this. So notice that this molecule is in a plane because of its conjugated pi system. So this black part is above the plane, and the white part is below, and it's opposite for the other side. Now, moving on from there, there are some other arrangements that are possible. And let's not forget to write in where the electrons would be. So because we have 4 electrons, we can, with paired up spin, because one pi electron from each of the 4 carbon atoms will be in this molecule. Now, the next 2 arrangements are pi 3 star and pi 4 star, and we will explain the stars in a second. So we have our 4 p orbitals, And we must draw now their phases. Now, a little hint about nodes. If we take whatever the subscript of pi is and subtract 1, we will get the number of nodes. So 1 minus 1 is 0, no nodes over here. 2 minus 1 is 1, and there is 1 node over here, and we'll have 2 and 3. And they are placed symmetrically throughout the molecule, or as symmetrically as possible. So with the 2 nodes, we will place them between these 2 molecules, or these 2 p orbitals, and with 3 nodes, they go all the way through. Now, the phases represent, or the combination of the phases can show these electron densities. So if we took, say, the pi 4 star, and we applied it to a real situation, we'd see that we would literally just have 4 different electron densities, none of them combining, none of them stabilizing. As you can imagine, they are extremely, it's an extremely inefficient arrangement based on energy. And that's why these arrangements, these unstable arrangements, are the antibonding orbitals. And electrons in these, or if electrons were to be in these orbitals, the molecule will be quite unstable. So we understand how to take this molecular orbital diagram and apply it to a molecule. But don't rush into those MCATs yet. There are still some things we need to understand. So, for example, say we had a molecule with the same conjugated pi system, but there was an oxygen that had a non-bonding pair. Where would we place the non-bonding pair in the molecular orbital diagram? Keep in mind one more thing, that the electrons present in this molecular orbital diagram are only the pi electrons, only the p electrons that go into the pi system. The other electrons can be accounted for normally with a regular molecular orbital diagram. So back to this non-bonding pair. The non-bonding pairs go into the n orbital, which is placed between bonding and anti-bonding. So we can just make one over here, and that's how it's placed. So for this molecule, as you can see, the HOMO, the highest occupied molecular orbital, will be the n orbital. And the LUMO, the lowest unoccupied molecular orbital, is over here, the pi 3 star. So with all of that, let's do an example and see where we're at. Say we are asked to draw the pi 3 orbital of 1, 3, 5 hexatriene. Now note that there's no star here. Again, the top half of all the arrangements are the antibonding, and the bottom half are the bonding. Because a molecule like this, which has more carbon atoms, as you can see, it has 6 carbon atoms, we can have more arrangements, pi 1 through pi 6. So pi 1, 2, and 3 will all be bonding. So for pi 3, let's just lay out all the p orbitals like we know to do, and now we know 3 minus 2, 3 minus 1 equals 2, so 2 nodes. Place them symmetrically, because that's how we place nodes, as symmetrically as possible, and then we will draw in the colors for phase. And now we have, with our 6 carbons, a few lows. So first the one over here, these 2 combine, these 2 combine, and these 2 combine. And we have 3 big electron densities. So when we draw our molecule and how it looks in the physical world, it'll look like this. Draw the electron density as it is. Draw the nodes where they are. So this is between 2 and 3, and 4 and 5. More electron densities, and the final electron densities. And that is how you handle molecular orbital diagrams for conjugated pi systems. So it looks like you're probably good to go, and you can keep that GPA in check and move on to Orgo.